Мы в эфире? Good afternoon, dear listeners. Today we'll finally do the final project of our numerical methods, and this will be the SOR method and Conjugate Gradient method. So we will start with the SOR method, and we want to solve the Poisson problem. And we know the exact solution, actually. It's given explicitly in our problem statement, and we will use it to define boundaries. Define Dirichlet boundary conditions. So that means that on your boundary, so we have a unit square. For example, it can be something like that. And here, let's use another color. For example, the orange one. And here, 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 and here, you use this function to define boundary values. And inside the square, we have a grid with a step delta x is equal to delta y is equal to h. And then we run it for different h and compare the results. Well, I will post the graphs somewhere here so that you can compare them. I won't post the number of iterations, but it can be somehow deduced from the graph. So what do we need to do for the SOR method? And actually, SOR method is quite obvious. You can, well, it's not logical to use Jacobi method with SOR because Jacobi doesn't update his values while he is going inside the loop. But the Gauss-Seidel, because of his updating values while he runs the code, the SOR method will give you some performance. And the SOR method is actually, you just use Gauss-Seidel, and you, instead of your last elements where you update your UHI with Gauss-Seidel, and here will be usual Gauss-Seidel. I don't want to write because it's ordinary. For SOR, it's a successive over-relaxation method for those who want to know what is SOR. You use the omega parameter, and actually you need to define it if you solve some other problem, but for the unit square with equal grid size, the value for omega will be 2 divided by 1 plus pH, I suppose. Yes, that's correct. And omega is a parameter which do the following. So you have your uij, and let's call this ordinary Gauss-Seidel formula, for example, Js. So that means that you calculate UJS with a scheme which you used previously, for example, for Gauss-Seidel algorithm, or you just Google how to use Gauss-Seidel and make it. If you need explanation how to do it, you can ask in the comments, but it's better to watch previous video where I discuss it in detail. And for SOR, you just do the following. You say that you use Gauss-Seidel with parameter omega plus uij, for example, the old one from the previous step, times 1 minus omega. We are back. And with the previous value, you use 1 minus omega parameter, and for Gauss-Seidel, you use the omega parameter. And omega is from here. and that's actually the whole algorithm of SOR. It will converge faster due to this omega parameter. Well, let's move on. And now the most interesting part, it's conjugate gradient method. And the idea of conjugate gradient method is not simple, but it's somehow similar to nowadays machine learning algorithms, where they use a gradient descent to find the local minimum of your function which you're trying to optimize. And here we will do something similar. We have our residual, which is equal to the difference between your function f and your approximated value. And here is a v, it's your numerical solution. And let's put here some like nn, which says that it's iteration n. And the idea of the conjugate gradient method is that we want to minimize our residual at each step, and therefore we want to move with the gradient of the residual. So we want to find a vector, find a direction at which we need to update our new solution so that our residual decreases the most. And I won't provide here the details. It will be maybe somewhere else you can read it, or maybe in summer I will post a lot of videos on the theory. Here will be the practical part, and the algorithm is following. First, you define your v0, and in well, you can define it any what? Like could be random. However, in our problem,
it's asked for
0u. So if you implement just conjugate gradient method, you can choose any values for your initial guess. But for our purposes of our problem, and just to compare the algorithms, we will put it as zeros. And then you need to apply boundary conditions. But then, like, it's a small step. Apply boundary conditions, which we can.
Okay, this one.
And then you calculate your residual. R0, which is equal to A minus. Oh, not A. It's F minus AV0. And here comes the funny part, where you need to spend a lot of time and understand how to implement this F and A, and actually R0 and V0. First, I will write the whole algorithm, and then I will explain how we can implement this complex matrix A and V and F and R, because in algorithm R, F and V is the vectors and A is a matrix. However, in Python it's kind of hard to make a big one array, so I will show how it's possible to do with a two-dimensional array. And what else are we doing? We said that Q0 and Q0 is a direction at which we need to update our value, our solution. We said initially that it's R0. And then you do the following. It's actually, it can be a loop.
Let's write a loop.
It's like pseudo code with not so much pseudo. Okay, we say that fp plus 1, so it's our next iteration. For example, when p is 0, it will be the first. The first solution, which is not our guess. we use our previous value. So it's very similar to gradient descent, and who learns something about ML, it will be somewhere similar. And then we update, we add our parameter, it will be alpha of p times some q. And q0 is calculated previously, but it's not q0, it's qp. And alpha p we will define now. We choose alpha not randomly in any theoretical, in any book actually, academic book. You can find why we need to choose alpha as following.
And it will be r, well, how to write that name?
So we take the norm of vector r at iteration p and divide it by, it's not a norm, it's a little bit adjusted norm by matrix A. And I forgot to say that actually our algorithm, conjugate gradient method, it only works, let's write with for positive symmetric matrix. For symmetric positive definite A. It's very important. It guarantees why our denominator will be positive and not zero. However, we will not prove it, and we assume that for 5-point rule, the matrix A is positive and symmetric. So alpha p is calculated as following. It's just a norm of vector r at iteration p divided by the following expression. And next we need to update our residual. And our residual,
at step p plus 1, it will be residual of step p minus our alpha times aq at iteration p. Then
we need to update our direction. We need to take new direction qp plus 1. As you see, at each iteration, we use the direction from previous step, so we update our direction at the end.
And it will be r plus 1, the new residual, plus the beta parameter, which we will clarify a little bit further, and times the previous value of q of p.
Where beta is a norm of r plus 1, and we can say it's like that, for example, divided by norm of iteration p. And I will repeat it one time more, that this expression, it's actually just a Euclidean norm of vector r at iteration p plus 1. And actually, that's the whole algorithm. And it can be shown analytically that after n iteration, where n is your dimension, where, well, let's choose another color. N is equal to, let's call like some Python, I don't know, it's pseudo Python, len of v convergence. So we converge at n steps, where n is your length of your array, or maybe the dimensions of your problem. So, and here we can see some troubles. First, we need to understand how to define matrix A and how to define all these vectors so that we can operate with them in Python. And mostly the problem is we need to write it in matrix-free form, which means that you cannot build first matrix A, which will be constant. You need to somehow you need to make all of these calculations without building matrix A. And this is the main challenge here. and we will do the following. First of all, well, put this algorithm to the here, to the top left. We say that we know how our matrix A acts on vector V, on our solution. Since we are using 5-point rule, we assume that, for example, let's index our vector V with 2 indexes. And then what we know that our scheme is the following.
This is from it's uxx plus the same for y. Oh yeah, it's interesting. I write some where to keep it the same, and this will be u by y, and we can simplify it a little bit. So it will be e plus 1j plus vi minus 1j minus 4ij plus vi j minus 1 plus vi j plus 1 divided by h squared. So
this is the action of our matrix A on vector Vij, and for example, Vij can be actually, we can write it, for example, as V if you want to use a 1D notation. For example, it can be like this, I times I big plus j, where I is a length of well, maybe it's better to say it's number of points for x direction. I suppose it can be converted like that, or maybe we should put I here. So. But it's possible to use this double notation to define 1D array. But the most interesting part is that actually now we have understanding on how our matrix A is supposed to act on vector V, on vector V. And then we need to notice the following. First,
and here I need to use red color.
This one, it's as I already said, it's a norm of vector r at iteration p, and what it's just a sum of each coordinate of each term of vector r squared. So it can be something like ri p squared, and we don't care whether it's 1D array or 2D matrix. So I will say that it's actually Rij, and let's put here letter k so we don't mix notations. And here we sum over ij. The same is true here. Similar. Now the only what we left with is this one.
And to do that part, what we see?
QP transpose when we multiply by A by QP. So this one is a vector. And this one is also a vector. Let's assume that this vector is which letter? For example, T. We don't use T. Then, similar to this one, it will be equal to QPK times TK. But as similar to the star, we can say that it's actually will be Qij times Tij if we use the same indices, the same notations. And now it became clear that actually we don't need to keep a 1D array, we can keep a 2D array. And only what is left is to calculate this one guy. But Tij is actually just this one. It will be the same Tij, because we just need to replace letter V with letter Q. And I will just put it here.
So
now we have the following. We have a 2D matrix Vij. Let's write it
here. What we have? First,
2D Vij. This step, I suppose, is obvious and everyone can do it, because you just need to assume your array. For example, you put it as zeros, and then you calculate your residual, and blah, blah, blah. So F we can also consider as a 2D array. 2D F ij, which will be equal, in our case, F is minus 2 sine y times cosine x. So it will be minus 2
sine yj times cosine xy.
2D. Then we have 2D R, which we calculate as following, as in the diagram. It's also 2D. And we also have a 2D Q. So actually, that's the whole algorithm. And I'm not sure that it was perfectly clear how to do it. However, maybe you should rewatch the video, try to implement the code, and then rewatch it again. Because as you can see, all we need in this algorithm is only two parts. First, we need to define and make the first step, and then we need to make iterations. And this one is until stop time, and stop time will be determined by your purposes. For example, it can be the difference between the old solution and new solution until some condition. Or it may be some other condition, maybe 1000 iteration. And the graphs for the conjugate gradient method you can also see right now. Well, as I said earlier, first you do one step, you calculate your residual at iteration 0 and your direction at iteration 0, and then you make the loop where you update your VP plus 1, RP plus 1, and QP plus 1, which is 2D arrays, and for that you either create a double loop, or you can use a Python sugar syntax, and it's very nice how the DeepSeek can do it. I recommend you use LLM for that. And you also don't need to forget about the alpha and beta parameters. So I believe it's became much clearer how to do it. And if you need to compare the solution, you can compare them. Thank you very much. Subscribe, like, and put something nice about our operator.